cosmology, they think, okay, that's going to be dark energy. That's what it's going to be all about. And certainly since the discovery of the accelerated expansion back in, 1998, that's been a big motivation for a lot of new supernova cosmology research. So a lot of new surveys finding new supernovae. The motivation has been to understand what's causing the accelerated expansion and to understand what's going on with dark energy, okay? And that's really parameterized in this single number here, this very special W here, which is the equation of state of dark energy. And I'm going to tell you guys a little bit more about that later in the talk, okay? But that's really motivated almost, I suppose, 2 decades now of research into supernova cosmology. It's to measure this number, the equation of state of dark energy, to higher and higher precision. And we're now at the stage where we have an extraordinary wealth of supernova data. And I think that there's a lot more we can get out of the supernova data than just W, the equation of state. And what's really made this interesting in the past few years is 2 of the most interesting cosmological parameters, most interesting cosmological tensions, are actually not related to this W, the equation of state of dark energy. So one of them is actually the amplitude of structure in the universe. The universe seems to be forming structure at a slightly lower rate than we might expect. And then also, perhaps most famously, there's this controversy between measurements of Hubble's constant, okay? And local measurements of Hubble's constant seem to suggest that the universe is expanding even faster still than we would expect in a universe dominated by dark energy. And what I'd like to focus on today is how we can leverage this extraordinary wealth of cosmological data to study a lot more than just W. So as I'm going through, obviously this isn't something Russell said, is that cosmology might be something a bit different. So please do shout out if you have any questions as we're going through, okay? But I'd like to start with a bit of background to sort of cosmology in general, okay? So when cosmologists, okay, that's a bit, I've got more background material than this, I promise. No equations allowed. It trips off some. We will try plugging it back in again. Oh. Shall we try the other projector? Should we try firing that one up? I'll try plugging this in and out, and then maybe we've got the backup projector if.
Do you know any cosmology jokes?
Tell you some cosmology jokes. It's oh, that's
really doesn't like that
it
equation.
really doesn't. I wonder if. I promise it's a perfectly reasonable equation. It's not. It's not. It's plugged into there. Should we try resetting the projector, maybe? Maybe you can, like, subliminally get the background material. Should we just go to plan B? Shall I?
Get behind it.
Yeah.
We'll move this in.
Okay. All right. Thank you, Russell.
I'll slide it back.
Yeah.
A little
Okay, great.
You're good?
Brilliant. Great. Okay, so it's a bit smaller, but it's not just blue. So I think that's probably we're ahead. So a bit of background, okay? So when cosmologists are talking about background, what we really mean is the background, okay? We mean the cosmological background, okay? So our model for the whole universe is essentially just, okay? So you guys might have seen that kind of analogy that, expanding space-time, it's kind of like a balloon expanding, okay? And really, in essence, that is what our model for the universe is, okay? It really is just essentially a homogeneous container of different fluids, and maybe these different fluids have different kind of pressures, they have different kinds of densities, and they're going to have gravity, and it's just a balance of different forces, okay? And that really is what we call the cosmological background, okay? So this line element here, this is the fundamental cosmology sort of line element that describes the background, okay? So essentially what we have here is just the metric for flat space, okay? And the only difference from purely flat space is we have this scale factor in here, A, so the cosmological scale factor. And what this tells us is how the universe is changing, how the sizes in the universe are changing with time, okay? So this scale factor A, it's a function of time, okay? And what supernova cosmology has almost always been doing is essentially mapping out what this scale factor is as a function of time, okay? So whenever we observe a supernova and we have a redshift of the supernova and we have a distance, we essentially have one data point on what this scale factor is as a function of time. So we can say the universe was a certain amount smaller at a certain time ago. That is essentially what a standard candle is giving us, okay? So whenever we're talking about the background, what I mean is any relationship where we're constraining the distance redshift relation. So what Hubble discovered back in 1929, okay? But as written here, this would be a very unexciting universe, okay? So this is a universe completely devoid of any features of any structure. It would not be a very fun or very interesting place to live, okay? So if we want to put some structure in there, to put some features in, one approach is we can perturb this background here. So we can squeeze in some small perturbations, okay? So we can do that like this. We can put some small perturbations to that time-like separation and some small perturbations to the spatial separations. So this really is just the metric for flat space-time with a scale factor for the spatial part and then some perturbations. And these perturbations are what give rise to all the structures, so all the galaxies, all the clusters, all the stars, all that good stuff which makes up space. That all arises because we don't live in a perfectly flat, unperturbed space. That space has some perturbations, and then that grows with gravity. And whenever we're doing observational cosmology and we're going out and we're looking where the galaxies are, we're going out measuring supernovae, maybe we're going and measuring gravitational lensing of galaxies or anything like that, what we're fundamentally doing is studying these perturbations. So these perturbations here, which have just perturbed the time-like part of the metric, we can study them whenever we're looking at things which are non-relativistic. So, right now we're not relativistic, okay? Maybe, if we're driving or something, we might think we're moving through space a little bit, but really we're only moving through time, okay? So whenever we're non-relativistic, if we're a galaxy or something like that, maybe the galaxy is going to have some velocity. It's nowhere near relativistic. It's only really moving through time. It's not really appreciably moving through space. So whenever we're looking at observations sort of like where galaxies are or how fast they're moving, we're constraining these time-like non-relativistic perturbations. On the other hand, some cosmological observations constrain both of these. So whenever we're looking at any cosmological observation, which is some sort of integrated observation, which depends on the path that light is taking from the source to when it's observed. We're sensitive to both of these perturbations. And you might often hear them being called space-like perturbations or relativistic perturbations, or sometimes lensing perturbations, because whenever we're looking at gravitational lensing, that's what we are studying there. And the reason that I like this framework so much as a way to test cosmology is because in the case that we have gravity described by general relativity, and the matter in the universe consists purely of cold, dark matter, these two potentials, these two perturbations, come out to be equal. So these two conditions here, that we have a universe of general relativity with some cold, dark matter, are really the fundamental assumptions of cosmology. We think we can describe the universe with general relativity, and we think most of the matter is only dark matter. So if these two potentials are equal, if this is the case, then we think that's okay for our standard model of cosmology. But if they're different, that's a kind of smoking gun that maybe some of the assumptions that have gone into our cosmological model might be incomplete. Okay, so maybe dark matter isn't purely cold dark matter. Maybe there's some interactions there. Or maybe general relativity isn't a complete description of gravity. Maybe there's some extra parts to it which aren't included in general relativity. So traditionally, supernova cosmology only probes this scale factor here, A. But we're in this situation now where we have hundreds and hundreds of beautiful type 1a supernovae. And what I'm interested in doing is saying, well, can we probe these perturbations, probe things which we don't usually think about measuring with supernova cosmology with this amazing data set that we have available? So I'd like to show you an illustration of one of the best compilations of supernova data that we have available. So this is an illustration of supernova from the Joint Light Curve Analysis Supernova Survey. So this is a compilation of about 740 different type 1a supernovae from about 3 different surveys here. So we're right in the middle there. This big wedge you can see here were supernovae from the Sloan Digital Sky Survey, so from SDSS. That's what that big wedge is out there. And then these pencil beam surveys are supernovae found by the Supernova Legacy Survey and by the Hubble Space Telescope. So they're nowhere near as big area, but they go a lot deeper. And what's great about this is that these 740 supernovae, they've all been analyzed jointly, okay? So the supernova parameters, so things like the light curve parameters, have all been fitted simultaneously. So we can kind of treat this as one supernova survey.
What's the color code?
Oh, okay. So supernovae have slightly different, have colors. Some are redder, some are bluer. So I've just sort of indicated that with the color. So the bluer ones are actually slightly bluer and the redder ones are slightly redder. So the main sort of thing that we would get from a supernova survey really are sort of classic Hubble diagram measurements. So really continuing directly in the tradition that Hubble started back in 1929. So measurements of distances from looking at the brightness at the peak of the light curve and some corrections compared to measurements of redshift. Okay, so we have redshift over here. So we're kind of over here towards redshift 0. And then out by redshift 1, that's about half the age of the universe, so about 7 billion years ago. And then on this y-axis here, this distance modulus, it's essentially the log of the distance, okay? So when we plot it like this, it looks approximately like a straight line. And we can see the different surveys that went into making this Hubble diagram up, okay? And this is the main product that you might think about getting from a supernova survey. And it's really this sort of diagram that's used to constrain the equation of state of dark energy. So whenever we're changing how dark energy might behave, or maybe we're changing the density of dark matter that we have in the universe, what we're changing is we're changing the distance redshift relation. And that's something that we can calculate essentially from the co-moving distance. So we're changing that, and it's something we can independently measure with these supernovae. And that's really how you would think about maybe measuring W with a supernova survey. But what I'd like to show you guys is what we get when we subtract off the best fit cosmological model from the actual observation, so the residuals. And it's really the residuals that where I think we might find the most interesting things. So on the one hand, if you're only interested in measuring W, you'd like as little scatter about that Hubble diagram as possible. All of that scatter, you're really just viewing that purely as uninteresting noise that you'd like to get rid of. So part of this scatter is just sort of due to noise, and maybe there's nothing too interesting there. But part of this scatter is actually coming from real cosmological signals. So especially as we get to lower redshift, the galaxies which these supernovae are in have appreciable peculiar velocities. And as we get to lower and lower redshift, those peculiar velocities represent a larger fraction of the observed redshift. So as we're getting to lower redshift, part of this scatter is actually coming from the cosmological peculiar velocity field. And as we go to higher redshift, there's more and more matter between us and the supernovae. And the more matter there is between us and the supernova, the greater chance there is that the supernova is going to be affected by gravitational lensing. So as we're going to higher and higher redshift, some of these supernovae are being affected to a greater or lesser effect by gravitational lensing. So buried in the noise of these residuals are some really interesting cosmological signals. So let's look in a bit more detail about where the lensing signal is coming from. So what I'm showing you in this plot is essentially a histogram of residuals of the Hubble diagram, okay? So whether the supernova is going to be magnified or demagnified. So this minus sign here, that corresponds to a magnification, and this positive sign here corresponds to a demagnification. So you can notice here that it's quite skewed, okay? And the reason that it's skewed is that most lines of sight in the universe, most lines of sight are going to be underdense. So if we pick a supernova at random, the density of the universe along that line of sight is going to be lower than average. The reason is because for every overdense line of sight we're going to have, it's going to clear out a greater volume of space. So there's an asymmetry between if a line of sight is going to be overdense or underdense. And those overdense lines of sight, if a photon is traveling towards that, they keep the light rays from the supernova more focused than average. And that actually leads to this magnification here. And then those supernovae which are sitting on underdense lines of sight, their light rays actually get slightly demagnified, and we get this demagnification here. So what we get is a skewness in the residuals. So on this side, on the demagnified side, some supernovae are being demagnified. But there's this very long tail with a very low probability of lines of sight which are increasingly highly magnified. And these correspond to supernovae which are sitting on the very rare dense lines of sight, which keep those rays slightly more coherent and keep the supernova slightly more magnified. And this skewness here actually contributes to the scatter. And by modeling it and carefully measuring it, we can actually extract some limits on how much lensing is contributing to the supernovae. And what that lensing tells us about is the amplitude of structure formation in the universe. So this is one of those controversial measurements where we think the universe is forming structure at a lower rate than we might expect. So let's take a look a bit more in detail about how we do this, okay? So I'd like to just spend a moment talking about moments, okay? So here we go. So a moment, So we've all probably heard of the variance or something. So that's just the second moment. So what we do is we take some measurement and we subtract off the mean. So we get some residual. And then we raise that residual to whatever power of the moment we're interested in. So the variance is just the second moment. And that skewness information is contained in the third moment, okay? So this to the third power. So what we can do is we can measure, instead of just fitting for the Hubble diagram, we can look at the moments of those residuals. And that actually has some information about whether the supernovae are being lensed or unlensed. So we've got another kind of Hubble diagram here. So again, redshift 1 over here going to redshift 0 over here. And what I'm showing you on this axis, this is the second moment, so the variance, and I've square rooted it. So it's the standard deviation. And what we can see here is, if we take a look at the peculiar velocities of the galaxies, at redshift 1, there's not a lot of peculiar velocities. Structure hasn't really started forming, and what peculiar velocities they have don't contribute a lot to the observed redshift. And then as we get towards redshift 0, as structures are growing, and as matter is falling onto clusters, those peculiar velocities are growing. So we see that the peculiar velocity signal shoots up as we get towards redshift 0. And then conversely, as we look to more and more distant supernovae, there's more and more matter between us and the supernova. So the dispersion coming from gravitational lensing increases as we're looking at more and more distant supernovae. So the combined effects of both of these is that the dispersion decreases here due to lensing, and then at some point, about redshift 0.3, the contribution from peculiar velocities starts increasing here. And that's what we get from the second moment of those residuals. So looking at that, it would be very difficult to disentangle the physics, what's coming from the peculiar velocities and what's coming from the gravitational lensing. But if we look at the third moment, so the skewness, we can actually start to separate these out. So if we look at the peculiar velocities, they don't introduce any skewness to the residuals. But if we look at the lensing, because remember there's that long tail of the lensing distribution, that contributes this characteristic negative skewness. So we actually applied this kind of analysis to the JLA supernova sample. So we measured the moments and we compared them to expectations based on the amplitude of the peculiar velocities and the gravitational lensing. So this is what we found, okay? So on this axis, we've got what I'm calling fluctuation amplitude, so sigma 8. And this is one of the cosmological parameters which tells us about the amplitude of density fluctuations. So it's telling us about the amplitude of those lensing and velocity perturbations from the background slide. And this is one of those cosmological parameters which is starting to emerge as slightly controversial. There's some disagreement between Dirac's measurements of it and expectations for what this parameter would be in our standard cosmological model. So I'm just plotting a likelihood on here. So the sort of fiducial value that we would expect for this parameter in our standard cosmological model with the 8, so over here, okay? So this is a very noisy measurement. You know, we're really trying to extract some signal that's buried in the noise of this data. But what I think is quite neat about this is that even with a survey that was designed to measure essentially the distance redshift relation, we can start to put some constraints on cosmological density fluctuations. So if we just said, okay, maybe these perturbations are only due to gravitational lensing, we actually get this very broad constraint over here on the amplitude of density fluctuations. And then if we're only looking at the effects of peculiar velocities, we get some upper limit on how much these density fluctuations could be contributing to that scatter. So we're saying we don't think sigma 8 could be as high as, for example, 2. Okay? So these are very broad limits on sigma 8, but we can lensing perturbations and density fluctuations coming from peculiar velocity fluctuations. And we can do this just with the noise that is buried in the data. So this was purely looking at the moments of the residuals. So what I'd like to show you now, these are the angular coordinates, so the RA index on the sky, of slightly more than 200 new supernovae from the dark energy survey. So we had our first release of results and papers from the dark energy survey supernova group last year. And of course, measuring W, the equation of state of dark energy, was one of them. And I'll show you guys that in a minute. But the thing I'd like to emphasize about these angular coordinates is that we've got 4 distinct patches, and they have quite dense angular coordinates. So we essentially have sort of 4 pencil beams here. So what this enables us to do is, as well as just looking at the moments of these residuals, we can actually look at if the residuals are correlated, if they have some angular correlation. And this is another signal that we would expect from gravitational lensing. So, for example, if this supernova over here is going to be magnified, then we would expect that this supernova over here, it's going to be sitting on essentially the same line of sight. We would expect it to be correlated. So what we can actually do is measure the correlation function of residuals from these supernovae and compare that to expectations for the correlation function, and use that as another way to constrain the lensing amplitude. Now, all of the supernovae in DES are higher than a redshift of about 0.2, so they're not really going to be affected too much by peculiar velocities. So for these supernovae, we're only looking at the lensing effects. So what we have in this plot here is the angular correlation function. So we've got angular separation here for pairs of supernovae, okay, going out to 20 arc min. So we're looking at quite small scale angular correlations here. And then on the y-axis here, we have the correlation function. So saying if we have 2 supernovae separated at a certain angular distance, how correlated are those residuals going to be? And this theoretical correlation function here is the expected lensing signal. So lensing introduces a very, very small correlation. It's a very sort of fine effect on those supernova magnitudes. And if we're looking at the correlation function, we can only actually put upper limits on how correlated it is. So we're saying it's less correlated than a certain amount. And the amplitude of this correlation function is set directly by sigma 8. But as well as doing this, we can simultaneously fit for the skewness due to gravitational lensing. So here, instead of angular distance, we've got redshift again. So redshift is 0.2 out to about redshift 0.5. And I'm showing you guys, so in red here, these are supernovae from the dark energy survey. And for a comparison, we have these independent supernovae here from the JLA analysis. And we can fit for the skewness and the angular correlation function at the same time. So even though we're just putting upper limits on the correlation function, when we combine with the skewness, we actually get some limits on the amplitude of gravitational lensing just from the residuals. So I can show you guys a similar plot, similar constraints that we see, okay? So what we have on the horizontal axis is sigma 8, so the amplitude of cosmological density fluctuations. And this dashed horizontal line, this fiducial value, this is what we would expect sigma 8 to be in a lambda CDM universe here. So we're still putting very broad constraints on sigma 8. But what I think is really interesting is that there's some, even though not at all, not very high statistics, but there are some upper limits on sigma 8, just coming from the noise, just coming from the residuals. So this is sort of suggesting that there's some evidence that the supernova in the dark energy survey and in JLA are being affected by gravitational lensing. So it's some sort of promising first signs that there's going to be a lensing signal in there. So in the next generation of supernovae, we're going to have orders of magnitude greater numbers. So hopefully that's quite promising that we're going to be able to get a more competitive detection of sigma-8. So that's how we can get sigma-8 from supernovae. But the other big parameter which has emerged as the big cosmological controversy is, of course, Hubble's constant. So before I get to that, you might be wondering, what about W? How do we measure W with supernovae? So W, it's one of those parameters that affects the distance redshift relation. And we would expect its value to be equal -1 if dark energy is what we call a cosmological constant. So the simplest explanation for what dark energy is. So something that we did with the cosmological analysis in the dark energy survey is we did the analysis blinded. So we did all of the analysis without seeing what the final values of the cosmological parameters were going to be. The idea here is to reduce confirmation bias. So this is actually a screenshot of the telecon when the parameters were unblinded. And this really is the live screenshot from the first time it was unblinded, okay? And this is the kind of raw terminal output of what we get here. And what you can see is W equals -1.002, okay? So really it's extraordinarily close to -1. And if I hadn't have been on the telecon myself, I'd be fair to say that you kind of might have been skeptical that the result came out so extraordinarily close to -1. But I'd like to emphasize that it really was done completely blinded. So we had no idea what this was going to be until this unblinding telecon, and it came out extraordinarily close to -1. And this plot was something that was generated automatically by the unblinding script here. So this parameter here on this axis is W, and this axis here is omega matter, so the density of matter here. So these contours here are what you get from the cosmic microwave background, and this grey contour is what you get from baryon acoustic oscillations here. And just indicating that the unblinding results just kind of sit extraordinarily close to that standard canonical lambda CDM values for the matter density and W. So in a sense, the most important result from the dark energy survey supernova program, so measuring W, is in some sense the least interesting because it is so extraordinarily close to just the totally vanilla standard value. So in one sense, that's amazing, and it's a really strong confirmation that dark energy is probably the simplest explanation of a cosmological constant. But of course, Hubble's constant has been emerging over the past few years as a lot more controversial. So we can predict what Hubble's constant should be in the lambda CDM cosmological model if we start with measurements of the cosmic microwave background. So especially the Planck cosmic microwave data set, and they can very precisely constrain the cosmological parameters from 13.8 billion years ago. And then if we have a cosmological model like lambda CDM, we can say, what would these parameters infer Hubble's constant to be at redshift 0, okay? What I'd like to stress about that, the result we get from Planck from looking at the cosmic microwave background, is that it's not a direct measurement. It's an inference of indirect parameters from 13.8 billion years ago, and then we have to infer a whole universe worth of physics to predict what Hubble's constant should be. And that predicts a value of Hubble's constant over here. So, about 67 point something kilometers per second per megaparsec. And what's really been led by Adam Rees by doing direct measurements of Hubble's constant is that they find a much higher value of Hubble's constant, so about 74 kilometers per second per megaparsec. And when this first began, I don't know, maybe about 5 years ago, it was still at the kind of level where maybe you could just kind of shrug it off, maybe it was just one of those things. But as the measurements on both sides have got more and more precise, this distance has now separated to, now kind of 4.4 sigma discrepancy. So people are starting to wonder, maybe these are the first hints of physics, which isn't directly included in lambda CDM. So maybe W doesn't exactly equal -1. Maybe there's some kind of extra relativistic particle. Maybe there's some curvature in the universe. Maybe there's some kind of interacting dark matter. And all of these would be an absolutely huge deal for physics. I think it's quite difficult to get models of inflation where we're going to get close to flatness, but not exactly. And then if we were adding in extra relativistic particles, these wouldn't be included in the standard model of particle physics. And then, of course, if W isn't equal to exactly -1, then that means general relativity isn't a complete theory of gravity. So in one sense, these all just look like maybe you can just twiddle some numbers a little bit, but they would all represent really big deals for physics. So what we thought about doing with the dark energy survey is how could we measure Hubble's constant with the new independent supernovae from the dark energy survey. So with all of these direct measurements here, we can't quite measure Hubble's constant directly just from the supernovae. So you've probably heard supernovae are standardizable candles. They're actually relative standardizable candles. So they don't give us absolute distance measurements. They actually give us relative distance measurements. And we can use those relative distance measurements to constrain the shape of the Hubble diagram. And that's how we can constrain W. But as we'll see, we can't actually constrain Hubble's constant directly. So the approach pioneered by Adam Riess is to calibrate the magnitude of type 1a supernovae based on more local Cepheid measurements. So we can measure the distances to Cepheids, we can cross-calibrate that, get the calibrated magnitudes to supernova 1a, and then take them out to further distances into the Hubble flow. So that's the standard kind of cosmological distance ladder approach. So you start with parallax to the Cepheids, and then you get the magnitudes to the 1a. So it's quite a clean, quite a direct distance ladder. It's really about as direct as you can get to get out into the Hubble flow. But you get this measurement Hubble's constant, which is higher than we would expect. So what we thought about doing with the dark energy survey is there a different way that we could calibrate the intrinsic magnitude of supernovae? And what we thought about doing is maybe we could calibrate that based on very far away distances. And instead of having a distance ladder, construct what we think about as an inverse distance ladder. So we've got some calibration at high redshift, and then take that back and see what the constraints would be. So this is the result that we found for Hubble's constant. So this is still looking at type 1a supernova, but calibrating them in a different way. And we get a very different value for Hubble's constant. We get this kind of lower value instead of this higher value. So I'd like to talk you guys through about how we can get this measurement and how it's sort of different to the conventional distance ladder, and maybe think a bit about what it might mean for the H0 controversy. So just a bit of the math that goes into this. So what we measure, as we've seen on those plots before, is the distance modulus. So this mu that we've been seeing on the plots, it's just the log of the luminosity distance. So that's something that we can kind of theoretically calculate, and this luminosity distance depends, we can calculate that by integrating Hubble's constant, and actually the Hubble's constant as it depends on redshift. So we can theoretically calculate the luminosity distance and get a distance modulus. And then on the observational side, what we observe for the supernovae is we observe the observed distance modulus depends on the peak magnitude of the light curve. So we see the light curve getting brighter, it reaches a peak, and then it starts to fade. And then we can also apply some corrections. So this correction here, it's called the stretch. So this depends on how long the light curve takes. And this correction here, it's the color. So depending on if the supernova is redder or bluer, we can apply some corrections to improve the distance modulus measurement. But the thing I want to emphasize here is that the intrinsic supernova magnitude that we observe, when we compare that to the theory, it's degenerate with the Hubble's constant that is sitting in that integral there. So if we only have supernova observations, we can't get Hubble's constant directly from that. We can get the shape of the Hubble diagram, but not H0 directly. So this is why usually you have to calibrate based on Cepheids. But what we thought about doing is, could we, instead of calibrating to standard candles, could we calibrate to very distant standard rulers? So what we've got on this plot here, again, redshift, not quite up to redshift 1, not quite down to redshift 0, okay? And on this axis here, we essentially have c times the redshift divided by the distance, okay? Now, this might seem a slightly convoluted quantity, but if you remember Hubble's law, Cz is h0 times the distance, what this axis is essentially telling us is Hubble's constant. And as you go down to redshift 0, that converges to Hubble's constant. So these are the kind of axes that we're thinking about. And the standard that we use to kind of go into detail about this here, but please do ask me after. So what that allows us to do is, by taking the inverse of that, we can place these standard rulers on this plot here. Then when we think about our supernova, they're relative standard candles. So we have some kind of freedom when we place them on this graph, essentially sort of moving them up and down, okay? If we didn't include the supernovae, these are the kind of constraints that we would get if we extrapolated these baryon acoustic oscillations down to redshift 0. So we'd predict an H0 slightly less than 66 kilometers per second per megaparsec. But what we're missing out on is we don't have any information below redshift 0.1. So essentially, to get down all the way to redshift 0, we have to marginalize over all of the freedom in our model. But when we add in the supernova data here, what we do is we essentially impose that we want the distances where we have baryon acoustic oscillations and supernovae to be the same, okay? And then we have direct measurements of relative distances that we can take all the way down to redshift 0. So when we also include these supernovae, we get a better constraint on H0 at redshift of 0. So this is now our combined model with the baryon acoustic oscillations and the supernovae. And that's how we get our H0 of slightly less than 68, okay? So my takeaway from this is that maybe before we start looking for exotic physical explanations of H0, like adding in extra relativistic degrees of freedom, adding in curvature, adding in extra parts of gravity, we should really think more carefully about what's going on with the calibration, what's going on with the kinds of supernovae, okay? And are those extrapolations that we're making going to be complete? Because what we find is if we calibrate with a different way and work back, probing a larger cosmological volume, we get a value for Hubble's constant which agrees extraordinarily well with the value we would get from the cosmic microwave background. So I'd just like to spend the last couple of minutes thinking a little bit about the future. And the future of supernova cosmology, it's really going to be dominated by this telescope here, the Large Synoptic Survey Telescope, which is currently being constructed here in Chile. And what's amazing about this is it's almost something like the SDSS, but just really, really amped up. So it's going to survey the whole sky every 3 nights, and it's going to find hundreds of thousands of supernovae. So instead of talking about maybe about 1,000 supernovae, we're going to have orders of magnitude more supernovae. So these things that we're thinking about now, where we are, looking at the residuals and really trying to put limits on the lensing, hopefully when we have orders of magnitude more supernovae, these kind of techniques will really start to come into their own and be competitive with other more established techniques for lensing and things like that. The other thing I'd like to flag up about thinking a bit more about the future is right at UNG. So there's also another telescope construction site right a few miles away from our campus at UNG. So we're having a new observatory being constructed at UNG. Our largest telescope is going to be 28 inches, and we're going to have a pretty good spectrograph on that. And what we're hoping to be able to do is actually get spectra of interesting transients. So my hope is that we might actually be able to get spectra of potential type 1a and get spectroscopic redshifts for them, get spectroscopic classifications. So hopefully we really could be able to get some interesting data right from UNG. So this observatory is under construction at the moment, and it's scheduled to open in the summer. The other thing I'd like to flag up about this is that if you guys do have relatively bright targets that you would like a quick spectra of, please do let us know, because hopefully we should be able to get a spectra of that pretty quickly, maybe even that night. So if you do have a kind of relatively bright target and you think, hey, it would just be great if we had a more recent spectra of it, or even a spectra to start with, or maybe newer imaging, in particular filters, we'll probably be able to get it for you pretty quickly. So please do drop me an email or come and chat afterwards if that's something that you might be interested in. So the last couple of plots I'd like to show you are just some forecasts for how well we might be able to push this kind of science when we have 100,000 type 1a supernovae. So this is another plot of the angular correlation function here. So angular separation, and then again the correlation function. And these error bars here are a forecast of what we might be able to expect from supernovae from the LSST. So if you compare that to a kind of zero, no correlation, we'd be able to get a several sigma kind of detection of weak lensing from supernovae in the LSST, and really start to probe the physics which is contributing to that lensing. So we can start to probe the gravity of the photons that are taking the path towards us, and maybe the physics of the dark matter which is going into that correlation function. And the last plot I'd like to show you is an equivalent kind of plot, but looking at what we might be able to get from peculiar velocities of the more nearby supernovae from LSST. So this is the power spectrum of density fluctuations. So it's just the Fourier transform of the correlation function. So it's another way of describing the statistical fluctuations in the universe here. So we have instead small scales on here going to really huge scales over here, okay? And we can place some constraints on this by looking at local peculiar velocity measurements. So current constraints on the matter power spectrum from peculiar velocity measurements kind of look something like this, okay? So we can constrain this sort of middle part of the power spectrum, but we really don't get very good constraints on this really large-scale fluctuations in the power spectrum. And these large-scale fluctuations, so scales larger than this turnover here, were actually generated in inflation. And these are modes in the power spectrum which are so large, they were generated in inflation, and in the whole history of the universe, they've never had a chance to evolve. So they were generated in inflation, and they haven't changed since then. So if we could measure the power spectrum on those really extremely large scales, we might be able to get some handle on the physics of inflation. So if we think about how well we might be able to constrain this with hundreds of thousands of supernovae from the LSST, this is a kind of forecast of how well we might be able to do. So we're really starting to constrain the power spectrum at those much larger physical scales. And that's something that we might be able to do with those peculiar velocities from the LSST. So my hope is that these techniques that we're starting to look at now with the peculiar velocities and the gravitational lensing, so we know that we can already place some kinds of limits on cosmological parameters from there. And then I think with the next generation, when we have orders of magnitudes more supernovae, they will really come into their own and give us competitive, independent constraints on these kind of cosmological parameters. So some of the physics we might be able to constrain, so at very small scales here, we can kind of constrain the physics of neutrinos. Larger scales, they're more affected by kind of modified gravity theories and the physics of dark matter. maybe even the effects of galaxy bias, and then the larger scales here are inflation. So really, at every scale, there's a lot of really interesting fundamental physics that we can constrain with measurements of the power spectrum. So this last image here, it's actually from a simulated realization of supernovae in the dark energy survey, so one of those deep fields there. So these red points here are the supernovae. And so we saw how they give us that amazingly precise measurement of W, minus 1.0002, okay? And I think they're going to continue to do that, and they're going to probe that distance redshift relation, and by calibrating them to baryon acoustic oscillations or Cepheids, we'll be able to get independent constraints on Hubble's constants as well. But what I'd like to emphasize are all of these blue points here. So these are galaxies along the line of sight. So what I want to emphasize is that these supernovae, they're not existing in a vacuum. They're being affected by all of the matter that's surrounding them, and some of that noise actually contains really interesting cosmological information. And if we treat that more as a signal instead of just noise, we can get some really interesting stuff out of it, okay? So if you do have any questions, please do feel free to drop me an email. This is actually my old email address, but it still works. If you switch that out to @ung.edu, I'll also get that. Or I've got a few more details on my website, or please do come and chat afterwards. So I think all I want to say now, thank you so much for inviting me over here to speak and hosting all of our students. And I think the last thing I want to leave you with is just to remember that supernova cosmology, it's not just W, it's more interesting than that. So thank you all so much for listening. Thanks. Great, thank you.
We have time for a few questions.
Yeah.
Yeah, so given the different assumptions that go into the CMB measurement for H0 and the supernova measurement for H0, what do you think is going to be sort of the best third method to try and resolve these two? So there, for instance, there was just a paper 3 or 4 days ago from the Megamaser cosmology project, and they found a value that was in between the two, conveniently, but closer towards the supernova value. Wondering what are your thoughts for the most promising methods to maybe test those independently?
Yeah, so I think long term, the kind of end game is going to come from gravitational wave standard sirens, because, and we've already seen this with the first optical follow-up. So what you can get from that is you can get the distance from the gravitational waves, and if you can get the optical follow-up, you get the redshift. So from a single object, you get the redshift and an absolute distance, so you don't have to cross-calibrate with anything else. So amazingly, their first value they got just from one object is like exactly 70, so it's like right in the middle. But kind of, it's like sort of plus or minus 10, so kind of everyone is happy. And I think that is the kind of, really the end game for Hubble's constant measurements, because you're also probing a kind of larger volume. The thing that's going to take is to go from plus or minus 10 to less than plus or minus 1. It really is kind of root n. So we're just going to need to find that many optical counterparts of standard sirens. And I think even in pretty optimistic cases for gravitational waves, it's going to take a few years to build that up. But yeah, I think long term, that's going to be the cleanest, most direct way to get H0.